In the first case, you see that the 7.7 microfarad capacitor is charged by a 125 volt battery and is then disconnected, and then it's connected to a second capacitor that has no charge on it, and the final voltage on each one is given as 15 volts. What's the value of the second capacitor? Now remember that what does not change here after you connect the two is the total charge. That's logic. Whatever the first one had is what both of them together are going to have, isn't it? Because you cannot create or destroy charges, correct? So first what you do is you're going to find the charge on the first one. Charge is given by, so I've called it Qi, which is C1V1, meaning first capacitance multiplied it by its voltage, and the final charge is going to be C1 plus C2. So is it connected? How is it connected? Series or parallel? Yeah, because if you only have two, how can you connect them in series? You cannot connect them in series. It has to be in parallel. You have a charged capacitor and you have an uncharged one, right? You're going to connect them with two cables. No. Both the sides, one side is going to be positive, the other negative. So that's not going to, that's why I've used C1 plus C2. And then that's going to be times the voltage, which is the final voltage. So that makes sense. Okay. And I told you that the charge initially has to be the same as the final. So put those two equations together. Now it's all math. Just rearrange to make what you have to find, which in this case is C2. So I'm trying to separate C2, which you can do after putting in the numbers if you want to. The first capacitance is 7.7 microfarad, 125 by 15 minus 1. You get it as 5.6 times 10 to the minus 5 farad, which is 56 microfarad. Okay. There I was trying to show another way of doing it, but I will not let that roll. Okay. Okay, let's move on. I think I should have given you more time, but look, it takes 15 joules of energy. Energy is work to move a 0.20 millicoulomb charge from one plate of a 15 microfarad capacitor to the other. How much charge is on one plate? Of course, both the plates will have the same quantity of charge, isn't it? So we're looking for the charge. The idea is work is the product of charge and voltage. That's how we have defined voltage. Remember? W by Q. So work is 15. The charge is 0.2 millicoulomb. That's why it's 0.2 times 10 to the negative 3. When you divide that, you get 75,000 volts. And once you get that, use capacitance is charged by voltage to find out the charge. Straight. It's a 15 microfarad. That's why it's 15 times 10 to the minus 6 times the voltage is 75,000. So the answer is 1.125 coulombs. But of course we had to assume something. What did we have to assume? In doing this problem, what did we have to assume? Yeah, that the charge is a constant. That moving this didn't alter the charges that much. Of course we moved a small charge, isn't it? So it doesn't. So that is the assumption that we are using. All right. So assuming that the charge does not change appreciably. Right? All right. Number 3. I could not put the question up there. Is that the intensity of the electric field given? The area in centimeters squared, change it into meters squared, of course, 10 to the negative 4. Distance in meters now. You're looking for charge. You have to know what intensity is. We used it today, sigma by epsilon naught, where sigma is the surface density of charge and it is Q divided by A. That's how it's defined. So E is Q by A epsilon naught. That's it. Make Q the subject. Rearrange. Substitute the numbers. That's it. Yeah, that's a point to be. It does not depend on the distance. You did not even need the distance. But remember that the intensity actually has distance in it, right? Although you don't see it there, doesn't intensity depend on the distance? Yeah. It's voltage divided by distance, so it's there, but you don't really need it in this problem to do that. Well, here are the problems on chapter 19. This is the first problem, and it talks about a 32 centimeter diameter conducting sphere charged to 680 volt relative to voltage is equal to 0 at R is equal to infinity, and says what is the surface charge density. Now, surface charge density is the charge divided by the area. So if you take the total charge and divide it by the surface area of the sphere, you're going to get surface charge density. And because the potential is given here, and potential is given by the formula kq by r naught. Remember that k is 1 by 4 pi epsilon naught that you see here. Now, so this is just k. 1 divided by 4 pi epsilon naught, all of it is k. So in effect, this formula is k q by r naught. Therefore, when you make q the subject, you get this, and sigma, which is the symbol for surface charge density, is q divided by the surface area, and for a sphere the surface area is 4 pi r squared. And so now when you substitute the value of q from here, the 4 pi's are cancelled, r naught and one of the squares here gets cancelled, and therefore you get sigma as simply v naught epsilon naught by r naught. Substitute the numbers that's given. Epsilon naught is called the permittivity of free space. It's a constant. And so you get the answer as 3.76 times 10 to the negative 8 coulomb per meter squared. In the B part, it says at what distance will the potential due to the sphere be only 25 volt? Now here in this case again you have the same formula as before, except that you are given the voltage. So like we did before, if you substitute back, you get this formula. From that, make the radius the subject, and we know that when it is 0.16 meter, the voltage is 680, right? V naught, and R naught is what you see here, and this voltage is 25, therefore the radius is 4.35 meter. That is the distance at which the potential will be 25 volt. Brings us to the next question, which talks about finding the electric field in the membrane wall of a living cell, and assume the wall is 10 nanometers thick and has a potential of 0.10 volt across it. Living cells really have a high electric field inside it, meaning the intensity of the electric field is really high. And the relation between electric intensity and voltage is given by E is equal to V by D. Remember that the living cell is just like two parallel plates with a voltage between them. And so D is the distance between those plates. In this case, D is the thickness, given as 10 nanometers, which is 10 times -9. And the voltage is given. So the intensity of the electric field is 10 to the power 7. That's 10 million volt per meter. That is the kind of field that exists in a living cell. This third question is really a tough one, and do not spend too much time on this if you do not understand it. But basically, what is happening here is a 25 microcoulomb point charge is placed 6 centimeter from an identical plus 25 microcoulomb point charge. How much work would be required by an external force to move a 0.18 microcoulomb test charge from a point midway between them to a point 1 centimeter closer to either of the charges? So in the first case, you have this 0.18 exactly midway between the two charges, and therefore the potential energy is given by, you can see K here, this is K, Q times Q divided by the distance, which is D by 2 because it's right in the middle, and plus, so this is due to the first charge and this is due to the second charge. But finally, when you move it 1 centimeter closer, I'm considering that you move it, the one here is the small d. So what happened now is it moves the little d distance closer to one of the charges, but at the same time that much further away from the other charge, right? Because it was right in the middle, and you move it by 1 centimeter towards one, so it gets closer to that one and further away from the other. Therefore, the final potential energy has this formula where you have the distance changing for both, as I've explained. And the work done is the difference in the potential energies. So the work done is UF minus UI. So you have the final minus the initial. Actually, the initial is the sum of two terms that are similar, so I put it as twice one of the terms, okay? Twice one of the terms. And then before substituting, I've taken out the common factor. The common factor here is this 2 times caps q little q by 4 by epsilon naught, and then here you have 1 by d minus 2d plus 1 by d plus 2d minus here the third term 1 by d by 2. Now, having obtained that, all you got to do is just multiply, and here you have 2, and then 1 by 4 pi epsilon naught is k, which is 9 times 10 to the 9, and then 25 is one charge, and 0.18 is the other charge, that's the caps q and the little q, and then you have, because both of them are in microcoulombs, and you have 10 to the negative 6 times 10 to the negative 6, so it's 10 to the negative 12. And then I've just substituted the numbers that you see here, and I get 0.34 joules. Again, like I said, this is not such a tough question. You just got to understand that when you move that charge towards one of them, you're doing work, and therefore the increase in potential energy becomes the work done. And in the fourth question, how much voltage must be used to accelerate a proton? The radius is given so that it has sufficient energy to just touch a silicon nucleus. Now you know that the proton is positively charged. The nucleus, the silicon nucleus, or for that matter, any nucleus is also positively charged. And therefore, when the proton approaches the nucleus, there is going to be a strong force of repulsion. And this repulsion can be overcome by using a high voltage. So that's the question, how much voltage do you need to just make that proton touch the silicon nucleus? And from the idea of potential, we know that if V volts is the potential, then the potential energy would be the charge multiplied by the potential, right? Charge multiplied by the potential is the work or the potential energy, which should be equal to the force, which is here. In this case, it's 1 by 4 pi, that's K, Q1, Q2 by R. This is K again, this is K, 1 by 4 pi epsilon naught is K, Q1, Q2. Okay, the silicon nucleus has 14 protons in it, that's why I have 14 times the charge of an electron, because electrons and protons have the same charge. And so when you rearrange that, of course one of the E's get cancelled from both sides, and then you just substitute this is K, which is 9 times 10 to the 9, 14, this is the charge of the electron or the proton. And then the important thing is to know that the radius is the sum of the two, because when they just touch, if that's the nucleus and that's the proton, when they just touch, you're going to have this distance plus this. So that's going to be the distance between their centers. That's how I've added. And then you get it as 4.2 million volts. Well, I don't think I was recording all this time. Somehow the sound stopped. Anyway, what is important in this problem is to realize that the total initial charge is equal to the final charge. And therefore you have these two and substitute it here, and then mathematically make C2 the subject. That is what I've done. I've divided throughout by VF and then brought C1 to the left side, and then substitute the numbers and you get the answer as 56 microfarad. And on the right hand side I've shown you another method of doing it, which is the voltage is total charge by total capacitance. So you can use either of the two methods to get the answer. In the fourth one, which is a real simple one, is this the fourth? I must say this was the sixth one. Yeah, in the sixth one, an electric circuit was accidentally constructed using a 5 microfarad capacitor instead of the required 16. Now, without removing the 5 microfarad, what can a technician add to correct the circuit? Of course, he can just add 11 microfarads in parallel, because then the total will become 16, right? So that's a simple thing. In the seventh question, two capacitors connected in parallel produce an equivalent capacitance of 35 microfarad, but when the same two are connected in series, the equivalent capacitance is only 5.5. What is the individual capacitance? Okay, when they are connected in parallel, you get 35. So C1 plus C2 is 35. And when they are connected in series, you get 1 over C, you know this, that's the formula, is 1 over C1 plus 1 over C2. Now you know that if there are only two capacitors and they are in series, you can write it as C1 C2 by C1 plus C2, which is what I've done. And then C1 plus C2 we know already is 35. So I've substituted there. Okay. So therefore, and that is given as what? 5.5? Yeah, so you got to see a 5.5 here. So when you cross multiply, you're going to get 5.5 times 35 is equal to C1 C2 times 1, which is what you see here. So you get the product as 192.5. Now that means you have two numbers which when you add you should get 35, and when you multiply the same two numbers you need to get 192.5. So you have two equations, substitute one into the other and solve them. When you solve them you get C1. You're going to get a quadratic equation which you solve, and when you solve them you get C1 is 28.2 microfarad, C2 is 6.8 microfarad, or maybe the other way around. In the 8th question, there is a 3500 picofarad air gap capacitor. That means between the plates you have no particular material, it's air, connected to a 22-volt battery. If a piece of mica is placed between the plates, how much charge will flow from the battery? Now, this piece of mica is a dielectric, is an insulator. You know that when it's inserted, the capacitance increases. And because the capacitance increases, it's able to accumulate a greater amount of charge. So let's work that out. The initial charge that it has would be the product of capacitance and voltage. But the final capacitance, you know, is K times the initial capacitance, where K is not 9 times 10 to the 9, please. K is the dielectric constant for mica. So the final capacitance increases as many times as the value of K for mica. And the voltage is constant. Why? Because it's still connected to the 22-volt battery. So now we know that the final charge is the product of the final capacitance and the voltage. And so you just take the difference between the two. QF minus QI is going to be the additional charge that's going to flow. Voltage can be taken out common and then substitute their values. Because, you know, I wrote that because CF is KCI, right? So in place of CF, I wrote K, and then I've taken the CI out. You can understand that. And mica has a K of 7, so that's why you find it. So it's 7 minus 1, and that's the initial capacitance, that's the voltage. So the additional charge that has flown is 4.6 times 10 to the minus 7 coulombs. Alright, in the 9th one, a homemade capacitor is assembled by placing two 9-inch pipe pans 5 centimeters apart and connecting them to the opposite terminals of a 9-volt battery. Estimate the capacitance, the charge on each plate, the electric field halfway between the plates, and the work done by the battery to charge the plates. Which of the above values change if a dielectric inserted? Again, an important question. Here you have the capacitor, and the value of capacitance for a parallel plate capacitor is given by this formula, epsilon naught A by D. Okay, so epsilon naught is 8.85 times 10 to the negative 12, and the area is pi r squared because both plates are pipe hands or circular, and this is, I've multiplied with 0.0254 to change it into meters. 9 inches is the diameter, so half of that, 4.5, is the radius. So right here you have pi r squared, but the radius has been converted into meters. When you do that, you get 7.265 times 10 to the negative 12 farad. In the B part, you have to find the charge on each plate, and that is Q is CV. Multiply the capacitance with the voltage. It is 9 volt, so you get this answer. And the C part, what's the electric field? As I told you before, electric field is the voltage divided by the distance between the plates. Voltage is 9. Distance between the plates is given as 5 centimeters, and 5 centimeters in meters here, so you get 180 volt per meter. And D, the work done to charge the plates. The work done is actually the potential energy of the capacitor, and that is given by 1/2 times Q times the voltage. So the charge on it, which we have already found, times the voltage. Which of the above values change if a dielectric is inserted? Surely the capacitance increases, the charge will increase, and the energy will change. Surely the electric field, in this case, does not change because the voltage and the distance between the plates both did not change. An electric field, you know, is voltage divided by distance, right? Those are the answers. And now the last one, the electric field between the plates of a paper separated capacitor is 8.24 times 10 to the 4 volt per meter. Let you see the whole problem. So you can see the question here. Electric field is given. The plate distance, is 1.95 millimeters apart. And the charge on each plate is given. Find the capacitance and the area. Direct question. Charge is the product of capacitance and voltage, but voltage is E times D, because E is V by D. And therefore C is Q by ED when you rearrange. Q is the charge given here, intensity of the field or the electric field is given, the distance in meters is here, so you get the capacitance. And because capacitance is K epsilon naught A by D, and K is 3.75, right? Just rearrange to make the area the subject. And when you plug in all the numbers, you get 0.283 meters squared. And so those are the answers to these questions, and some of them are really important, and try to learn them. Thank you and good luck.